Hello. Continuing with our discussion on the kinetic theory, in this video we shall start with the van der Waals equation of state. Now, the real gases deviate from the ideal behavior at high pressure and low temperature, that is near the liquefaction. And a molecular analysis of this deviation was made by J.D. van der Waals, and what he observed, he arrived at the modified equation of state for real gases in the year 1873. And the assumption about the size of the molecules and the interaction made in the postulate for kinetic theory of gases was modified. So what were the modifications? Now, first up, the correction was made for the finite size of molecules. Now, as far as the finite size of the molecules were concerned, now the molecules were assumed to be point particles, point masses, and the actual volume of the molecules was neglected in comparison to the volume of the container of the gas. But in reality, the molecules are not point particles and have a finite size. Now, in order to make corrections for the finite size, each molecule is treated as a hard sphere, and let's take the diameter as d. And so the centers of two molecules cannot approach each other within this distance. Okay, just as we had given the condition for mean free path, we had shown that if we have two molecules over here and the centers will always be separated through a distance d, because d is the diameter over here, so d is the distance of separation. They cannot be closer than this distance d. And so for this pair of molecules, a sphere of volume 4 over 3 pi d cube, it constitutes the excluded volume which is not available for motion. Now this is the volume that is not available for motion to this pair of spheres. Now you can consider a pair of spheres here. Obviously they are molecules. Now you can consider the surrounding as well. Everywhere I have drawn one on top of the other. Now we can consider the side molecules, which will obviously be maintaining the same distance from these given spheres or molecules, and as a result of that, this entire sphere of that given volume 4 over 3 pi d cubed, that won't be available. So the volume that is excluded per molecule will be half of it. So for two molecules, if it is 4 over 3 pi d cubed, then for one molecule it will be 4 over 3 pi d cube halved. That is exactly what I've written. So now the volume of each molecule, with d being the diameter, so the volume of each molecule will be 4 over 3 pi, because d is the diameter over here, so d over 2 cube, which is obviously 1 over 8 times of this 4 over 3 pi d cube. Now if you observe, what we get is that excluded volume, the relation that we get, excluded volume per molecule, is actually 4 times the volume of a molecule. When you compare these two, you will get that kind of a result. Now this excluded volume of So this is for the case of the molecules, a pair of molecules. Now the excluded volume for 1 mole will be much greater. So the excluded volume for 1 mole of the real gas is equal to 4 times the volume of 1 mole of molecules, which is quite straightforward from what we have obtained till now. This excluded volume per molecule, per one mole of the gas, the excluded volume per mole of the gas is termed as co-volume, and this is usually represented by the symbol B. So for n moles of real gas, here n is in the degree of freedom, here n we are taking as the number of moles of real gas. What we'll be getting is that the excluded volume will be equal to n times of the excluded volume for 1 mole, that is n times of B, which is the co-volume, or n times of the co-volume. And so the ideal gas equation, which was PV is equal to nRT, will now change to P. So this was PV is equal to nRT, the ideal case, but that has changed, and that has changed to P. Instead of V, we will be excluding the volume. So that's the volume correction that we were looking for, considering the finite size of the molecule which we have taken into account. Now prior to this, we had considered the molecules to be point masses, but now we will be we'll be considering their volume as a whole, and we will be considering the exclusion of the volume from the given container which contains the gas. Supposedly it contains n number of gases. So now we have the correction as P multiplied with V minus NB instead of only the V term in ideal gas equation. So this is V minus NB is equal to nRT. Now the co-volume is just the characteristic property of each gas. So the value would be different, obviously, for different gases. Now let's consider the case of correction for the attraction between the molecules. So if we were to consider, let me write that down first, correction for attraction between the molecules. Now the ideal gas equation was derived under the assumption that the molecules move as independent free particles and there's no intermolecular force. But the presence of attractive intermolecular force is demonstrated by the tendency of all gases to condense to liquids at low temperatures. So at these temperatures, the potential energy due to the mutual interaction overcomes the kinetic energy of the molecules. So the correction for this molecular attraction is made in a semi-empirical manner, and well, due to this mutual attraction, a given molecule draws its neighboring molecule towards itself and tends to hold them together. When a molecule moves towards the wall of the vessel, it experiences attractive force due to other molecules behind it. So it hits the wall with less momentum, and hence the pressure becomes less than what would have been in the absence of intermolecular force. So the pressure with no intermolecular force is given by P is equal to nRT over V minus NB, which is quite straightforward right from this equation that we have over here. But due to the presence of intermolecular, this is when we are considering no intermolecular force. Remember, we had obtained the expression for pressure using the kinetic theory postulates, and we had obtained the value of pressure previously to be different. But now the case being that of the intermolecular forces coming into account or considered in this case, then things will change. Let's say there's a drop in pressure by del P. So with the intermolecular force, let's assume that the pressure is now equal to nRT over V minus NB minus the factor del P, where del P is the reduction in the pressure due to intermolecular forces. There are n moles of the gas in the given volume V. That is the V we have considered, the total volume of the container. The number of moles per unit volume. So that's going to be N over V. And each molecule approaching the wall experiences attractive force due to the other neighboring molecules. And the number of such molecules is proportional to N over V. Now further, the number of molecules striking the wall per unit time is proportional to N over V as well. So by decreasing, the decrease in the pressure del P will be proportional to the square times of the number of molecules per unit volume. Decrease in pressure, that is del P, is proportional to the square times of the number of molecules per unit volume because of the factors that we just discussed. And as a result of that, let's put a constant term over here which is equal to, let us say, A times of N square over V square. That is what we are getting when we are considering the case of the correction in pressure. Now A is also a constant over here, and that is also characteristics of the gas that is under consideration. So finally we have the expression for P over here to be equal to nRT over V minus NB, and then we have minus of AN squared over V squared. And if we just put these things together, rearrange them, we have the van der Waals equation of state for real gases that we discussed earlier in our introductory, or maybe the second video, I don't remember exactly, but there's somewhere there. So this is P plus of AN square over V square, that is the correction in pressure, and that is followed by V minus NB, which is the correction in volume, and at the right hand side we have the regular nRT, which is the number of moles multiplied to the universal gas constant times the absolute temperature. So now A and B are known as the van der Waals constant, and these are arbitrarily adjustable parameters. And if you look at the units of A and B, A has the unit of pressure, so pascals, and meter raised to the power 6 and divided by mole squared, while it is meter cube per mole in case of B, that is the co-volume. So for 1 mole, this equation would change to, with N being equal to 1, P plus A over V squared, and multiply to V minus B only instead of NB, and at the right hand side we'll have only RT. So that's for 1 mole. Now let's discuss some features related to the van der Waals equation. Now if we consider the van der Waals equation, it is a two-parameter equation of state. In addition to the P, V and T, we also need the parameters A and B to know the equation of state of a gas, to know the state of a gas. That is the equation already, and its deviation from ideal behavior. So with the equation that we had at hand for a unit number of moles, that is n is equal to 1, we can have the pressure term to be equal to uh, RT instead of nRT, V minus NB it was, now it's V minus B, minus, that was n squared times of A, now it's just A over V squared. So this is for n is equal to 1, we are considering number of moles being equal to 1. Now if we solve this, what we get is we can just cross multiply them, and what we are going to get is V cube minus V squared times of B plus RT over P plus V times of A over P minus AB over P. This is going to be equal to 0. Now as you can see, this is a cubic equation, which suggests that V will have three roots. V will have three roots which correspond to the values of V for each P. Corresponding to the values of V for each P. Now what are those P terms that we are considering? The case being, we can refer to the previous graph that we had considered, the pressure volume graph, and in that case you had the isotherms, and with those isotherms you had three such cases where you had the we had the uh, two states, that is they were lying equally in those dashed lines. If you can go back to the graph over there in the previous video, and we had made that the pressure versus volume, we had considered the isotherms, and we had obtained those parameters or those points where it is lying in a mixed state of vapor and liquid, those dashed lines, just the previous one. And if you look at that, you will have the points corresponding to different pressure terms, and those corresponding pressure will yield different volumes. And well, that is the case that we see over there, is that the gaseous region and the liquid region will be fine, but it is about those dashed lines which had a mixture of vapor and liquid. The curves obtained from van der Waals equation will behave differently from those experimental curves. For each pressure, there are three values of volume satisfying van der Waals equation, which is quite evident from what we have obtained over here. Now next we aim to relate the critical constants with the van der Waals constant. Now we already know about the critical constants, the PC, VC and TC, and the van der Waals constant just we obtained as the co-volume B and the constant A. Now for the unit mole consideration, we have P is equal to RT over V minus B minus A over V squared, and if we were to differentiate both the sides, we will end up with dP over dV to be equal to, and on the right hand side what we'll get is RT over V minus B squared, and for the second term we have that to be equal to 2A over V cube. Now differentiating that further, what we'll be getting is d2p over dv squared. That will equate to 2rt over v minus b cube, and this one now will become minus, so 6a over v raised to the power 4. Now at critical points, v is equal to vc and t is equal to tc, p is equal to pc. Now since the critical point is the point of inflection, that is maxima or minima of the curve coincide there, so at these values what we get is the first derivative as well as the second derivative must be equal to 0. Now with those values being 0, let's put them and let's check for these constant values that we have obtained. So for the first one, if we look at it, then we have 0 on the left hand side, and then onto the right hand side we have r times of tc instead of just t, and down below we have vc minus b whole squared plus 2a over vc cube. Now as for this equation, what we get is 0 again, and over here we have 2RT, 2RTC now, over VC minus B whole cube minus 6 times of A VC to the power 4. Now what we can do is, because there's a negative sign, we can put them on one side and keep the other one right at its own place, keeping the terms positive. So what we do over here is that we take the RTC over this side, VC minus B whole squared, and this is now 2a over vc cube, and in case of this one we have 2rtc that stays on its side, and the other one can go to the other side. We are getting 6a over vc to the power 4. Now if we take the ratio, suppose this is the first one and this is the second one, and we divide 1 by the 2, then what do we have? This is equal to. So in this case what we are getting is, we'll be having VC minus B on one side, and then on the other side we'll have a VC for sure, and that divided by 3, and this will be actually 2 VC because we have a factor 2 over there. So this will be 2 VC over 3. Now with this thing available to us, what we get here is, with this we get the value of Vc to be equal to 3b, or b is equal to Vc over 3. Now if we are substituting this equation of Vc in the previous one that we have taken over here, so we put this value of Vc there, and what we get is RT, that is Tc, over 3b minus b whole cube is equal to 3a over 3b raised to the power 4, and that gives us Tc, which is now equal to 8a over 27 times of Rb. We'll give this a separate equation. This is probably equation 3. We take it as 3, and this one we take as 4 for future references. Now with all this, we can put the values that we have obtained in 3 and 4 over here right at the top in this case. So we get PC now to be equal to RTC Vc minus B minus A divided by Vc squared, and that is equal to, we put the values of Tc and Vc in that. What we obtain is, you'll check for yourself, I have tried it in my rough sheet. So this is A over 27b squared. So this is a over 27b squared, and therefore we have the relation, that is, let's take it as 5 because we have named them, or we have numbered them. So this is 3, 4 and 5. They are giving the values of the critical constants in terms of the van der Waals constants. Conversely, if we wish to obtain the van der Waals constant in terms of the critical constants, we can have them. Now from this equations that we have obtained, we can take a simple ratio, And what we can do is we take Tc over Pc, and that goes to 8b over r if you look for that. Now, therefore, B will be equal to R over 8 times of Tc over Pc. So we'll be requiring two of them. And similarly, if we are taking Tc squared over Pc, then we'll be getting that to be equal to 64a times of 27r squared, and that will result in the value of a, which is equal to now 27r squared over 64, and over here we have Tc squared over Pc. So this is mostly in terms of Tc and Pc as the critical temperature and pressure. Remember, the volume, the critical volume is the volume that is occupied for a gas at the critical temperature and pressure. And the critical pressure is obviously the pressure that liquefies the gas and at the critical temperature. Now, with all of this, we have obtained the relation between them, but now we wish to reduce this so that we get rid of A and B, because they are not going to be the same for all the gases. Now, this is not universal. This equation that we have obtained, that is the van der Waals equation, that is not going to be universal, because different gases will have different values of A and B. Now, in order to obtain a universal condition or a universal equation which satisfies or is valid for all the gases that we may consider, we can consider a separate case that is known as the reduced equation of state, which we will be discussing right now. Now, as I indicated, that we need to consider the universal manner, and in order to do that, if we express the temperature, pressure and volume as the fractions of their corresponding critical values, then the constants A and B will be eliminated out of the equation. And because the fractions are because they are fractions, obviously they are called as the reduced variables, and the equation of state thus obtained is known as the reduced equation of state, which we will be obtaining right now. So the reduced pressure will be, let's say it is PR, and that is equal to P over PC. Now you may wonder that we are getting a dimensionless quantity on the right hand side, but what I said, if you notice, is that we are just dividing, because the critical pressure will have a particular value to it, and that is why that is just a number term. So we are just dividing or reducing the pressure of the given gas by the value of the critical pressure. We are not dividing the pressure by pressure, but the value of the pressure, and as a result of that, this will be in fractions, of course, and the value will be reduced, but the dimension won't be lost. So pressure, reduced pressure in this case, is the pressure over the critical pressure. Similarly, we have the reduced volume as well as the reduced temperature. So the reduced volume now is V over Vc, and that of temperature Tr is simply T over Tc. Now if we are replacing this, so what we get is P will simply be equal to Pr times of Pc. Same goes with the value of V, and same goes with the value of T, which is equal to Tr times of Tc. With these values available, we can change the van der Waals equation for a unit mole. We get, for instead of P, we have Pr times of Pc minus we had the value as, this is not minus, this is plus, so this is NaN going to 1 divided by V squared. Now V squared is a Vr squared times of Vc squared, and on to that second term we have Vr times of Vc instead of V, and the co-volume term B subtracted from it. And on to the right hand side we have R times of T now is equal to Tr times of Tc. Now we substitute the values of the critical constants that we had obtained prior to this, that is for Tc, Vc and PC. We had obtained those values. If you can recollect, this is PR, it stays as it is. Now for PC we had obtained it to be A over 27B squared. You can just refer a few minutes back into the video, just the previous page. And then over here we have a VR squared. Now as for VC, we have the value to be 3B, and when that is squared we have 9B squared in this. So we have put the values there. Over here again we put the value 3B for VC, 3B times of VR minus B, and onto the right hand side we have R times of TR, and the value of TC, as we know, is 8A over 27 RB. So with these values what we get is from the first term we have A over B squared to be taken as common. So we get PR over 27 plus A over 9VR squared, that is what remains. In the second term we can take a B to be common from both the terms, so 3 times of VR minus 1, and onto the right hand side we have A over B as well. Now this B cancels out with one of the B's over here. This is RTR 8A over 27 RB. Now the A cancels out with this A, and the B remaining cancels out with this B, and we are clearly, no, this is not A, this is 1. We are clearly yes, so we have clearly got rid of those constant terms that we had. Now this 27 over here can get multiplied to the other side, so we'll be having just PR over here, 27 multiplied to that, and for the second term we'll be having a 3 over there divided over VR squared. So this is the first term, and for the second term we have 3VR minus 1, and on the right hand side we just have 8 times of TR, with of course the R term cancelled out. We have just 8 times of TR over here. So this is now the equation, the reduced equation of state, which does not contain the parameter, that is what we had is A and B extra parameters, which were changing with respect to the kind of gas we were considering. Now this is a universal nature, this equation. It is of universal nature and is applicable to all the gases. Now this equation will lead us to the following important relation in the behavior of different real gases. If the values of any two of the three reduced variables, that is PR, VR and TR, are identical for any two real gases, the value of the third reduced variable is also the same for the gas. So this is the statement of the law corresponding to the states for the gases. Now the critical coefficients, that is the ratio of RTC and PCVC, is known as the critical coefficient. That is RTC over PCVC, and that is equal to R times of TC, as we know it, as 8A over 27 RB multiplied to this. This has been taken in the reverse way, or reciprocal of it, for PC, and now for VC again we have 1 over 3B over here, and this is equal to 8 over 3, which is just a constant term, which is 2.67. The theoretical value of the critical coefficient is a constant number independent of A and B, right? The value of critical coefficient is different for different gases and is more than 3 for most of the gases experimentally obtained. Now, having discussed all of that, we can consider the limitations of the van der Waals equation now. Now, the van der Waals equation can have the limitations that the equation of state for each isotherm that we had considered in the PV curve below the critical temperature has a maximum and a minimum, but the experimental observations show that the horizontal part without any maximum and minimum. And the van der Waals constants are supposed to be constants and have the same values for all gases, but they differ from gas for different gases. Even to the same gas, their value change with temperature. And according to van der Waals equation, the value of the constant B should be Vc over 3, but experimentally it was obtained to be Vc over 2, while the value of the critical coefficient that we just discussed, theoretically it was 2.67, but for most of the gases it is coming out to be over 3. It exceeds the value of 3, which differs greatly uh, for different gases. So these were some of the limitations of the van der Waals equation. You can take note of that. I've just dictated that. Uh, Mainly three basic points related to the isotherms, as well as the case of the critical constants, and the value of 3 or 4 points maybe. So these are, but because we have obtained the reduced equation of state, so we probably would not look into the problems faced in van der Waals equation. This is quite applicable for all of the gaseous systems that we can consider. Now, this finishes the theoretical analysis of the kinetic theory and the various equation of gases. We'll be trying a few numerical problems in the upcoming videos if possible. We'll try and squeeze in a few videos with numerical problems as well. So till then, thank you for watching.